There, the red light's lit, good. Okay, today we start off with 126. We will then, we start off with 140. We will then segue into, wait a minute, no, we start with, what is today, Thursday? Yeah, 140 to 126 to 145. So 140, ladder logic. Okay. One of the things that we mentioned yesterday is that when we talk about industrial schematics, we're not talking about the same type of schematics that we would discuss in a circuit-based world, electronics world, where we might have a circuit that looks like this in the electronics world. And 120 volts. We'll just write it as 120/60, 120 volts, 60 hertz, through a switch to a light bulb. This is what we looked at earlier on, and in fact, we may just replace this with a resistor and call it R1. R1 can represent any number of things. In this case, it represents a light bulb. This is the way we would represent that circuit in, say, 120. Yes?
120?
Oh, no, my dentist will kill me. I can't eat that stuff, but thank you.
It's not sticky.
Oh, yeah, that's what I told her last time.
I'm good, thank you.
120 or 120 version for your 120 class. And the 140 version of that will be hot, neutral, it was called LR1 for lamp resistor 1 or whatever, red, and then switch 1. Hot rail, neutral rail, we typically call this one L1. And we typically call this one L2. What does the L stand for?
Load,
Nope.
line,
Line. Okay, we generally refer to this, when somebody says line voltage, they're usually talking about 120/60. When somebody says, do you have a line cord? They're usually talking about one of those cords that goes in the back of a computer. It has the 3 prongs and the 3 holes. So when we talk about line, we're talking about the source of our voltage, which in this case is pretty much all the time going to be AC, and it's going to be 120, at least for our discussions here. Okay, so what we do is we have this group of rails that represent all of our power source. Okay? Now, when we look at this over here, when we look at our lights, what we have is we have a row of 5 switches. Do you see the row of 5 switches over there? Here, let me turn the camera so that even the people playing the home version can see what I'm talking about. I'll just turn this around right over there, and we'll zoom in on the 5 switches that are just underneath that oscilloscope handle. Okay? Those are the 5 switches that we're going to talk about. You guys see them, right?
yes.
Okay. Well, what are those 5 switches? Well, let's look at switch number 1. I'll turn it off. I'm not going to deal with the camera, but we see that switch number 1 turns on and off 1, 2, 3, 4, 5, 6, 7 light fixtures.
A row.
in a row, right? So here's what we're going to do. 1, 2, 3, 4, 5, 6, 7. Switch 1 turns on LR1, LR2, LR3, LR4, 5, 6, and 7. Underneath that, we have switch 2. And I've run out of board. But switch 2 turns on and off the second row of lights. So LR8, LR9, etc. And we would have a really tall ladder with 5 switches, each switch controlling 7 lights. However, there's one thing, Dawn, that I want to make sure that you understand. This is not the whole picture. This does not tell you where the lights are.
Yeah.
Where the lights are will be in your 104 class and will be based on what those guys do over there. If you look at what those guys do over there, they do layouts where they'll have this room laid out with dimensions and everything, and they'll have the lights listed or shown in the room. 7 times 4, 28, is it 4, 5, 7 times 5, 35 lights. They'll all be labeled. What's wired to which switch will be indicated in terms of the physical layout or the assembly or the elevation, if you want to call it, whatever you want to refer to it as, of that room. You can see all of the positions. This simply details the electrical hookup without any regard for placement. There's got to be another document that says physically, where is that light, where is that switch?
One of the things I didn't like about ladder logic, and I can make my point right here, is that unless you take this wall apart or you know what the panel is, you actually don't know that all the lights in this room are on the same circuit.
That's
You
right.
know
Well,
that
yes,
the power
you do.
comes into the same box, but they could be on separate circuits, because you can only run so many lights on one circuit.
But then that would be a different ladder logic diagram.
But that's what
then.
I'm saying, is actually to like draw this out, you
Mhm.
don't know that there's only one circuit in that box right there.
No, and from this standpoint, but you would from the ladder logic diagram. You would know that, because then you'd have a bigger picture where there was more than one hot rail. Right? So you might have something like this. Let me see if I can just squeeze all this crap in here. Right? Here you have a hot rail with a fuse or a breaker. And then over here, you have another hot rail with a fuse or a breaker and another neutral. And you've got 2 ladder diagrams, each one having 7 or 5 switches. But the truth is that this is really a poor example of what a ladder logic diagram is. Because, yeah, it's a ladder, but there's really no logic. Okay? We haven't really talked about any functionality here. And that's really what separates ladder logic from just a standard electrical drawing, is that a standard electrical drawing, like a schematic from last term, you're kind of always looking at the same flow of current. We didn't really deal with a whole lot of switches. And we certainly didn't make these things think, did we? But when we talk about ladder logic, the thing we have to ultimately concentrate is on the logic. that's involved. So let's put up another ladder logic drawing, and I'll show you a little bit more about where this comes into play. There's one drawing in the book that they slip it in there, but they don't explain it very well. Okay? And what we see is we see something that looks like this. I forget what page it's on. It really doesn't matter since you guys don't have your books in front of you anyway. You have a switch, like so, that goes to a control relay. Here, let me grab one of those. Here's a control relay, brand new in the box. Have a look.
Now defective.
Now defective, yeah. I can't see myself, it bugs me. Turn this around. And I'm going to explain what that control relay does as we move forward. We're going to look at a new symbol today. It's going to be very, very confusing to you guys.
At least he's upfront and honest.
We'll call that CR1. We'll call this CR1-1 and LM1. Switch 1. That was a nice S. Thank you for that. What is that?
It's your relay switch.
What's that?
Line 1 relay switch.
This
But
one?
it's not closed. Nope.
This one. You know what that is, Dawn?
It looks like a capacitor.
Yeah, that's where
It does.
Oh,
And that's the mistake that most
Mhm.
students that have never seen this before will make. Say, okay, you got a capacitor there.
But only
It is
because you
not.
have CR1, I know it's not a capacitor.
Right. It is not a capacitor. It is a set of contacts. Okay? Here's what's going on. Let me.
Normally open.
And we're going to talk about this in more detail, but yes, normally open. Here's what's going on. Let me kind of draw this up magnetically for you. Okay? I'm going to take my control relay, and I'm going to just call it a box. You've got one sitting in front of you, right? And let's call this terminal 1, terminal 2, terminal 3, and terminal 4. Just for the purposes of this drawing. Here's terminal 1, here's terminal 2. Terminal 1 and terminal 2 constitute an electromagnet or a coil. Here's 3 and 4. When I apply energy to the coil generates a magnetic field that pulls against the spring and causes this plate to move over and make contact here. Okay, so the spring then stretches out and it closes these contacts. This one kind of shows you how it works. You can look at this and see exactly what's going on. You see the magnetic coil. You guys can look at that together. You can see the magnetic coil. You can see sets of contacts. And that one has two sets of contacts. It has one set that's normally open, and it has another set that's normally closed. Okay? You see how that works? It's just like a relay. So switch 1 controls the coil of this contactor. And when the coil is energized, what happens to CR1-1?
It closes.
This closes, this one opens. So when I press down the switch, this light goes on, this light turns off. When I let the switch up, we go back to the original condition. And there's what we call a timing diagram. When switch 1, I should put SW1. It's the only switch there, so I guess it is there, but it's SW1. When SW1 is turned on, LM1 turns on, LM2 turns off. Okay, do you see the difference between this one and the other one, where we looked at just the simple lights? That there's a number of relationships that are developing here, where one light turns on and the other light turns off. We don't have that situation over here. These switches directly control those lights. One switch, one light, on and off. Here, a single switch is controlling more than one process. Each of these lights, and keep that in mind when you look over at the board over there, there's 4 lights on that board. Those aren't just lights, those represent anything we want them to represent. We could use one light to represent a motor, we could use another light to represent a heater coming on, or a transport belt coming on, something like that. We use inexpensive light bulbs to simulate the response of expensive pieces of equipment. So that way when you guys screw up and make things work backwards, the worst thing that can happen is that we lose a light bulb. Okay, so it's good for beginners. All right, fairly straightforward. Let's look at another example, and this is the example that I kind of want to pick on the book about. That really doesn't explain this at all, but it's very simple. I know you don't like me using that word, Dawn, because simple is as simple does, right? Oops. Okay, where's the energy, kids? Here's the energy is in red. These are all of the places that are hot. Right? That's where our 120 volts is. This is L1, 120 volts. This is L2, this is our neutral line. So we have a whole bunch of energy that would really like to get across that diagram and get over to the neutral line. But right now there's no path to get there. So what are we going to do? I need you to
Close the
pay
switch.
attention to this next step. So when you're both ready, I will continue because I need you to watch what happens. You ready?
Mm-hmm.
Okay. 1. Depress SW1. What happens when we depress SW1?
Current flows.
Coil energizes. When the coil energizes, what happens? CR1-1
Closes.
and CR1-2 close. That allows energy to go here, and it allows energy to go here, and LA1 comes on. Step 5 is release SW1. When we release SW1, this goes away. Notice that the light stays on at this point.
So it's kind of like acting like a push button.
It's acting like a latching switch. What we've done is we've latched it so that it works like a, yeah, well, not all push buttons are latching though.
Yeah.
But yeah, it works like an on-off, like a switch like that. It has 2 actual positions. It gives it 2 different or stable states.
So now how do you turn it off?
Ha ha! We can't.
That's what I thought.
I was waiting for somebody to ask that. We can't turn this off. Once we turn it on, it's going to stay on until we remove power. We actually had it set up like that over here at one point. But what we would do to alleviate that is we'd probably have to tear down a wall somewhere because my proper planning wasn't there. Give ourselves a little more room for our 120 volts. And put a normally closed switch in there. And we would label that stop, and we would label that start. Now, what you'll see is we'll talk about that later on. Actually, you guys will see this in the lab, that this then becomes what we call a dominant stop circuit, because the stop is before the start. It has to go through the stop before it gets to the start. Okay, but what this is a latching circuit. It allows us to turn something on by pressing a button and lock that condition, even though the button here, the start switch, has been released. we created another path around it, which is maintained even after we release that start button. That is the diagram. Actually, I'll tell you where it is. I think it's in the second chapter, second unit.
It looks.
What's that?
It looks kind of familiar, what I was looking at last night.
It's on page 17. If you look at page 17, here, I'll put it up here for you. Play around with this stupid thing again. What? You coming on, or what?
There you go.
I don't know if you guys can see this or not. This is the circuit that they show in the book. It's similar to this one. You'll notice here's a start push button with the latching contact. And then the emergency stop, or the stop button, comes after that. There's an emergency stop, and then there's another limit switch here that allows us to stop. In this case, the start circuitry is first. It has to go through the start circuitry before it gets to the stop. So this is what we call a dominant start circuit, as opposed to a dominant stop. And you'll see this in the lab. This example, the stop comes first, then the start. This example, the start comes first, then the stop. See the difference? Mm-hmm. This is a slightly different circuit, but yet it does have the same thing. Here's a normally open contact, a normally closed, and a normally closed contact. So when you push the start button, this relay is activated. This opens, turning the red light off, turns on the run light, turns on the motor. And then we have an overload switch, which you guys will learn about also, that protects the motor if it gets too hot. That will open, it's kind of like a fuse. But nowhere in the book do they really explain, especially this early on, what all this is about. They're just giving it an example, and it seems like every quarter.
To me, that emergency stop looks like, you know, if you have an emergency and you hit it, and it's going to shut the whole thing off.
Yeah, that's what happens. Although a lot of times, personally, I like to see my emergency stop buttons up here.
Yeah, I was gonna say, that's where they normally are. Because usually if you need to stop something, like you said, you want to stop it all. Then you can go back and figure out if something else can be, you can turn it on by section. But
And on the Army DED generators, you had the start switch, which is your S1 switch, your synchronizing switch, and then your big old red stop switch right in the middle.
Yep, and we have those sitting over there. I guess the reason they did it this way is because with this particular emergency stop here, it turns off the motor, but it doesn't turn off the stop light. The stop light will stay on, will remain on to indicate that there's still power going to the device or to the piece of equipment. That could be their possible reason for that. Because the lights aren't what's going to give you a problem. What's going to give you a problem is the motor. That's the only reason you would really turn or you bust the emergency stop is if somebody get their hand caught in the motor, and in that case you don't really care whether the light's lit or not. So, you know, it kind of does its job, but it's not as complete as it could be. You know, and that's something that the engineer has to decide. Do I want to put my emergency stop here so that I will have a red light to indicate that there's still power to that machine and there's still a hazard? Or do I want to put my e-stop up here so that everything is shut down?
so when you look at this,
Oh, I know what he's doing.
is this is considered to be non-energized? When you initially look at a ladder logic, it's considered to be non-energized, or is it considered to be energized?
In a ladder logic diagram, what is shown is referred to as the shelf state. Are you familiar with that term?
That looks like it's energized. What I'm saying is that LS1 switch,
This one?
open,
The light switch?
it's open, right?
It's not
Your-
open now.
Your CR1-2 is normally closed, and that when it's normally closed, that red light is gonna be on.
All right, here's what's gonna
And then
happen
once
when
it-
we push the button.
Once that motor runs, then the green light comes on and the red light will shut off.
Yeah, as soon as we press this, this closes, right?
Mm-hmm.
CR1 turns on, we have this
Yeah,
closes,
closes.
and we can release that at that point. Now we're latched,
Yeah.
right?
Mm-hmm.
This opens, which turns this off, that's what I have, where I have this.
Mm-hmm.
This opens, this one closes, turning the light on, and closes, turning the motor on. Okay, so you have a green light probably that says that we're running, a red light that says that we're stopped, and the motor and the green light are tied together. When one happens, the other one happens. Okay, but to answer your question, Dawn, when we look at the initial conditions, that's what we call shelf state. And shelf state means that, like that one's sitting right there.
Yeah.
You know, the normally opens are opened and the normally closed are closed.
Yeah, that's what I thought, but I thought I'd make sure.
Okay, so that's pretty much what I wanted to talk about today, is just give you guys a little bit more of this ladder logic, because you ought to be finishing up with the first couple labs where you're identifying switches and whatnot. It's time really soon to get over there and start wiring. So you guys are going to want to get over there and start wiring. You have like 20 different labs to do in that lab book that involve exploring that board, and I want you guys to get started on that.
Quick question, the first lab we have is the,
Switch identification?
no, it's the, oh, I cannot think, I cannot.
The
read
safety
it.
portion.
The safety, thank you, yes.
Oh,
Yeah.
yeah, light a lot on
Is-
me then.
But
Yeah.
there's, what do you want us to do? Do we just walk you through it? Because there's not like questions to answer, it's the lab is the procedure on what you want us to do. So
The
you want us
lab
to-
is find out where the energy comes from, identify all of the sources, where this energy comes from. And what I want you to do with that, and I'm going to change the lab eventually to reflect this, is I want you to figure out where all of the voltages are and what voltages there are in this entire lab. In other words, where does this voltage come from? Where's the source? We know it comes from
The
the
panel.
bench, right? But where does it ultimately come from?
The
Does
panel.
it come from that panel? So we have to know where that panel is, right? We have to know where these things are.
Even if we can't get in it.
Even if you can't get in it, but there is a number of the person that you have to call, you know, to get in there if there is an issue. But really, that's the first lab, is to identify where the sources are. And for us, you know, we've kind of boiled this down to simplicity because we're just plugging it into the wall for now. But at some point, those really should be conduit. There should be conduit, and those panel boxes should be fed by conduit from the box on the wall if you're going to truly be industry model. But we're not there yet. So for our practical purposes, our power comes from a plug-in in the wall. So the first lab in there is something you should read. It's a little bit moot because we really, you know, in the previous school that I taught at, they actually had to go down a basement or up in a wall in a crawl space type area to find where the power went. I made them do that. I don't have access to all of the nooks and crannies here. Obviously, everything's locked up. At the previous school where I wrote this, I didn't have that. I could go anywhere and do anything. It was a private school. So some things are going to have to change, but you have to be familiar with how the switches work. There's a switch identification lab, and then it starts getting into the actual wiring. And I'd like you to get to that wiring part sooner rather than later, because I don't know how long it's going to take you guys to do it. This is the first quarter that we've done this.
Well, I think our first two labs is, one is the safety and the next one then goes into the constructor program, to build ladder logic.
Yep, which is right over there. It's on that computer there. But what I'm looking for is this. The labs that are in this lab book. Lab 1.1, switch identification. Lab 1.0, which is out of sequence, switch identification. Lab 1.2, simple switching logic. You're going to ask you guys to do ladder logic, and
That's 140 or 145? I can't
140.
remember. 140. okay.
yeah, that's what we just
I
got
always
done
mix the
talking
two
about.
up.
Okay, so I need you guys to get cranking on those
Well,
140
you
labs.
just took our lab day yesterday.
Yeah, well, now we have a place to work. Wouldn't have done us much good without it, would it?
Nope.
Okay, any questions before we move into 126?